Hello, students, and welcome to another online lesson. Today we're going to be talking about normal distributions. Normal distributions are sort of a bell-shaped curve, and we'll look at some images of that. And we'll be finding probabilities for normal distributions with and without technology. We'll know we're successful when we can efficiently solve problems involving normal distributions with and without technology. So, what is a normal distribution? Well, normal distribution is for continuous data. So continuous, we've talked about that. That is data that is measured. So we can talk about time, we can talk about weight, size, anything that can be measured, volume. For some variable, x, some random variable, and we represent the mean. We've often used mean as an x with a line over it, but for this type of mathematics, they don't use the x with a line over it. They use what's known as the lowercase Greek letter of mu. When you write that, it almost ends up looking sort of like an M, um, or sort of a fancy lowercase u with a extra little hook there. And again, it's pronounced mu, like M-U, like music, mu, and standard deviation of, and we've seen that before on our calculators, standard deviation being lowercase sigma. There's this notation that we probably won't use much, but x meaning our data, n meaning normally distributed, and then it gives you the values of your mean and your standard deviation. So that's a way that they can write that information. So if we have data that is standard or distributed normally, then it has this bell-shaped curve, and we can see that here. In the middle of the bell-shaped curve should be the mean, and we see that represented here with mu. Think about like manufacturing or something like that. Let's say we were manufacturing bottles, and we would expect that, if it's, for example, a 12-ounce can of soda or something like that, that most of the bottles that we ship should be right around 12 ounces, if that's what I'm advertising it as. But due to the nature of manufacturing, there's always going to be slight variations, even with machinery and stuff. And so you may find that some are a little bit more than the 12 ounces, or some are a little bit less than the 12 ounces. Now, most of them would be right here at that goal target, most of the data, and we have indicated that data by having the bell-shaped curve be high there. And then as we get further and further away from that mean, or that targeted value, we get smaller and smaller and smaller. You'll see this happen with heights as well. The average height of a person, we could look, and most people will be right around that average height. Are there people that are taller? Sure. But as you get further and further away from that average, it goes down and down in either direction. Now, if it's truly normally distributed, and again, they would have to tell us that it is, then there are certain percentages that go along with the distance that we are from the mean. And we measure that with the standard deviation. We've talked in previous lessons about how to find the standard deviation. Now we can use that to measure how far we are away from the mean. So based on this picture here, what percent of the data lies within one standard deviation of the mean? So again, here's the mean. That's where the majority of my data will be close to that value. If I go one standard deviation to the right, I should find I have approximately 34.13% of my data. If I go one standard deviation to the left, subtracting one standard deviation from the mean, I should also find that it's symmetrical and I have 34.13% of my data. So the question is, how much of my data is within one standard deviation in either direction? So basically we say we have 34.13 in one direction, and we have 34.13 in the other direction. And if I add those things together, I'm getting approximately 68.3 roughly. 68.3% of my data is going to be within one standard deviation of the mean for normally distributed data. Now, what if I do two standard deviations from the mean? Well, I already have this 34.13%, but I'm adding on an additional 13.59%. And so if I add those together, I and I do it in the other direction as well, so I add up all four of these numbers, I'm going to be getting, and you can check my work here, but approximately 95.4%. So most of your data is within two standard deviations. 95 over 95% of it. And then when we talk about three standard deviations, that's very little data right over here in addition to all the other stuff that we've had. And if we add up that 2.15% in either direction, in addition to our 95.4% that we had for our two standard deviations, we will have over 99.7% of our data is located within three standard deviations. So these numbers are good to know. The IB syllabus says that we should recognize that within within one standard deviation, it's 68%, and then within two standard deviations, it's about 95%, and three standard deviations, nearly 100%, 99.7%. So that's the idea of doing it without a calculator. And I'm going to sort of jump around with my terms and notation, and let's take a look at a problem dealing with that. So the weights of babies born at Prince Louis Maternity Hospital last year averaged 3 kilograms with a standard deviation of 200 grams. So we can sort of highlight that information here because that's going to be important, our mean and our standard deviation. If there were 545 babies born at this hospital last year, estimate the number that weighed, part A, less than 3.2 kilograms, and part B, between 2.8 and 3.4 kilograms. For most of these, what you're going to want to do is draw a picture to sort of represent the normal distribution. So I'm going to do that here. Again, it's a normal bell-shaped curve. I know that right smack dab in the middle is going to be my mean, which is mu. In this case, I know that the mean is 3.0 kilograms. I also know that the standard deviation was 200 grams. A kilogram is 1,000 grams. So if I have 200, what would that relate to in regards to 1,000? 1,000, and that would become 0.2. So it's 0.2 kilograms. So if I were to add on one standard deviation here, plus one standard deviation, and that would be about here, I would now be, I would take my 3.0 plus 0.2, which would be 3.2, and that would get me one standard deviation away. And I could do another standard deviation away, which would get me to, so that'd be plus 2 standard deviations, and that would be 3.4. And then I didn't really leave myself enough room here, but I'll correct that. And then if I go a full 3 standard deviations, that would be 3.6. Going in the other direction, if I take away one standard deviation, right about here, I would take away from the mean, again, 3.0, take away 0.2, I have 2.8. And then I could go again minus 2 standard deviations, and I have 2.6. And last but not least, take away 3 standard deviations from my mean, and I'm left with 2.4, all of these being kilograms. So we want to know the number that weighed less than 32 kilograms. Less than 32. Well, we can shade here, and if I go right down the middle, that's 50% of my data already, because I cut it in half. So everybody who's less than the mean, that's half my data. Anyone who's more than the mean, that is also half my data. Here we're looking at 3.2 kilograms. So already I've got 50% of my data all the way to the left. But then I also have one more standard deviation to the right to get me up to 3.2. So I'm looking at all these people who are less than 3.2. Again, I already know that that's 50%. Plus, we know that from that previous chart that we had, one standard deviation to the right, we said, was 34.13%. And if I add those percents together, I'm looking at approximately 84.13 or 84.1 if I round that to 3 significant figures. So that's my percentage of babies that were born at this hospital that were less than um, 3.2 kilograms. But that's not what it asked. It asked for the actual number. If it said the probability, I would say there's an 84% chance, approximately of weighing less than that amount. If they want to know what percentage of the babies, again, I've got that, 84.13, but they want to know an actual estimate of the number. And if we go back here, it says that there were 545 babies born. So if we take 584, I'm sorry, 545, I don't know where I got. So 545 babies born, and then we multiply that by, there's the 84, by the 84%, and I'm just going to move the decimal to make it a 0.8413. And if I multiply those things together, I get 458.5, so I'm going to round that up to 459 babies. So for part A, 459 babies. And that would be using a normal distribution curve without technology to help find probabilities and percentages and values. Now let's take a look at part B. It says between 2.8 kilograms and 3.4 kilograms. Well, we know that, I'll shade with a different color. I'll use the red here this time. 2.8, that's one standard deviation to the left. And we know that there should be, again, 34.13% between the 2.8 and our mean, which was 3.0. But I also need to go to the right, and I have another standard deviation to the right, which is going to be another 34.13, plus one more standard deviation to the right, and that value is going to be 13.59, we said on the previous slide. 13.59. So I'm going to take all of these, add them all together, and we get sorry, calculator error. Let's try this one more time. Get 81.85%. 81.85%. So approximately 81.85% of those babies were born within that weight range, but we want to know what percent of the 500, or what was the actual number that represented the 81.85%. So I take the 545 babies that were born, turn my percent to a decimal, and when I multiply that, I get 446 babies. All right, sorry for all the dead space in this as I'm calculating while we do these. So again, that's an example of using no technology, just using that graph from the previous slide and assigning values here. Again, the picture is very helpful. Now we can also do these with a calculator. So I'm going to go back to my terms of notation here. Normal distribution with a calculator. If I'm trying to find the probability that x is less than a certain value, and it doesn't matter whether they say less than or equal to or just less than. On our calculator, we go to normal CDF. You find that under the distribution menu, which is on your calculator. I'll show it in just a moment, but it's right below the down arrow with the second key. Second, and then right below the down arrow, it's the VARS key. It's abbreviated DISTR, D-I-S, I'm sorry, D, yeah, I-S-T-R is the button that we use. And that will get you to that menu, and you scroll to CDF. There's 4 things you type in. You type in essentially what's the lowest possible value, and we're basically saying the lowest possible value is negative infinity. We type negative E, and we find that E on the calculator by pressing the second key and then the comma. So negative E99, which means just all the way to the far left of the number line. And then whatever value you're trying to find, that's your highest value in this particular case. and then you separate that with a comma with your mean and then your standard deviation. If we're trying to find a value that is greater or greater than equal to some number, that means that number will be the lowest one. We type that in first after normal CDF, and then we do E99, which means we just go on forever towards infinity. Again, we get the E by pressing second in the comma, and then our mean followed by our standard deviation. They're in alphabetical order. So your lowest number, your highest number, your mean, and your standard deviation. And then if we have a specific range of values, like the second problem we just did, again, normal CDF, and then we put in our lowest value, we put in our highest value, and still followed by the mean and the standard deviation. So it's the same thing every time. Normal CDF, our lowest value, our highest value, the mean, standard deviation, all separated by commas. So 4 numbers that we're entering. And again, if there is no highest number, we use E99 to represent positive infinity. And if there's no lowest number, we use a negative, not a minus sign, but a negative sign, E99, to represent negative infinity. So let's take a look at some of these. To start with, we have just a bunch of values here, given that x is a random variable that is normally distributed. They tell us the mean is 120, and the standard deviation is 15. Part A says find the probability that it's between 105 on the low end and 135 on the high end. Got a calculator here that I'm going to pull up. I don't really need it for this first one here because the first one, you'll notice that if I have standard deviation, a normal distribution, and then my mean is right here, and in this case our mean is 120, and if I go one standard deviation higher, I would be adding on 15, and so that would get me up to 135. If I go one standard deviation lower, 120 minus 15 gets me to 105. So I already know the answer to part A. It's just the probability is going to be 68.3%. And that's to 3 significant figures because we know it's within 1 standard deviation in either direction. Now, if we talk about the probability that x is less than 105, this time we're only looking at all this stuff here to the left. If it was the entire half, we know that's 50%. But we're taking away the 1 standard deviation here and just leaving all this other stuff over here on the left. So I'm going to take 50% minus, and then I've got my 34.13%. And if I subtract those, I am left with 15.9 roughly. 15.9% would be the answer here. So there's a case where subtracting can help us out. Again, where is the 34.14 coming from? That slide we had 2 slides ago where I had the big normal distribution graph and I had all those percentages listed there. Where did the 50% come from? Again, the mean is always sort of the halfway point. And so everything to the left of that would be 50%. I don't want all of it. So I took away the part I didn't want, which is the 34.13%. Greater than that, well, once I know this answer, 15.9%, if I want greater than 1.5, I would take the whole graph, 100%, and take away the part that I've already figured out, which is the 15.9%. So now I'm basically figuring out everything that's not shaded, which would be all this stuff here that I just covered in blue, everything else. So I take the 100% minus the 15.9%. And that answer would be 84.1 roughly. And then so on and so forth. So those are values where we didn't need to use a calculator. Now let's do some where we do need to use the calculator. Probability of 150. Well, actually, I take it back. 150 we could do without the calculator as well, because if I add 15 onto the 135, that would get me up to 150, which is 2 standard deviations away. And again, we could follow the same pattern that we did for these previous ones. But I'm going to skip ahead now to part E. 100 is a little bit more than one standard deviation below the mean. If I went exactly one standard deviation from 120, 120 minus 15 leaves me with 105. That would be one standard, but this isn't 105, this is 100. And again, one standard deviation higher would be 135, and this isn't quite one standard deviation higher. So let's use our calculator now to show how we could figure that out. So on the calculator, again, we're doing part E here. I'm going to go to second key and then distro, or the vars key, second vars, and you'll see our very second option is normal CDF. Normal CDF. That's the one we're going to be using exclusively here for these probability problems for normal distribution. I'm going to press enter. Another thing to remember is the first thing we put in is our lowest value. In this case, the lowest value we have is 100. So I type 100. I separate that with a comma, which is found right above the 7. My highest value is 130. Separate it with another comma. Then we put our mean in, and the mean we were told was 120. And then we do our standard deviation, which is 15. Now, before I hit enter, I just want to see if we have sort of an estimate of what this would be. Again, we said that 100 was a little bit more than one standard deviation to the left, and we know that'd be about 34, or a little more than that because it's more than one standard deviation. And we said that 130 was a little less than one standard deviation, but again, if it was exactly one standard deviation in both directions, we'd be looking at about 68%. So if we're somewhere in the family of 60 to 75%, I think we're reasonable. If we're not there, then I think we have an unreasonable answer. So let's hit enter, and we get 65.6%. Again, it's written as a decimal here, but just move your decimal over, and again, we can see that we have 65.6% for that one. All right, let's try doing F. Now we've got one that's the probability that our data is less than or equal to 140. So again, we go to second vars, number 2, which is normal distribution. We put in our lowest value. Well, this time it says that x is less than 140, so 140 is the highest value. Remember, think back to when we first learned about less than and greater than signs back in middle school. The big mouth eats the bigger number. So the 140 is the big number. So nothing is bigger than 140. So they don't tell us the lowest number. So we could go all the way down to 0 and beyond to negative infinity. The way we said to do that was put in a negative sign, second, comma, and there gives my E that I was talking about earlier, 99. That's basically saying negative 10 to the 99th power, which would be negative 1 with 99 zeros after it. So a very, very, very small negative number, comma. Then we put our highest number in, which in this case is 140, comma. Then we put in our mean, which is still 120, and then our standard deviation, which is still 15. And again, we could do estimates like we did before. We know that 140 is greater than the mean. The mean would separate half the data, and this goes about a little more than one standard deviation beyond that. So we're looking at somewhere around 90% would be my guess. And voila, we have 90.9%. If you're like, I don't know how Mr. Peacock got that estimate so quickly, again, you get better at it the more that you do with the hand, and then you have a better idea what you expect to see on the calculator. We'll do one last one. Part G, it says find the probability that we're greater than 125. Once again, second vars, and so we go to normal CDF, and this time we put in our lowest value. The little mouth on the greater than sign is eating the x, so the x is the bigger number, so the smaller number is 125. So we start with the 125. There is no highest number, and so we use the second comma for our E again, 10 to the power of 99, so a big old number as our highest value because we don't know what it is, comma our mean, 120, and comma our standard deviation, which is 15. And again, 125 was just barely more than the mean. So this has to be less than 50% because we have less than half the data would be greater than 125. So maybe somewhere, around 40%, give or take. And yeah, it's a little less than that. So 36.9% of our data would be located above 125. And we can do the same thing for the 80s. So that's the idea. We did it with technology. We did it with technology pretty quick, pretty easy. And as we know, we can use our calculators on all of the IB exams. So we need to be able to make sure that we can at least do it with the calculator. Page 303 and 307, we'll find 3 problems on each. Ones with technology are on 307. Ones without are on page 303. Good luck, ladies and gentlemen.